Welcome back. In this video, we are still in section 2.5, and we're still talking about work, but we're going to look at a new type of application, and that is the application of the work needed to pump water vertically, so to pump it up out of something. And we have an example here, example 5 from your notes. It says a cattle trough, which you can see here in the image, has a trapezoidal cross-section with a height of 1 meter, horizontal sides of 1/2 meter and 1 meter. Assume that the length of the trough is 10 meters, as you can see in the figure. How much work is required to pump the water out of the trough to the level of the top of the trough when it is full? So that's key. It's going to be a full trough. And the way we want to think about this is similar to the chain problem we did in the last video, where we thought about, there's this full chain, but we thought about it as a small piece of the chain and how much work it takes to pull up each little small piece of the chain. But in this case, we're going to think about it as a thin layer of water. So we have this full trough. This trough is full of water. But if we take a thin layer of the trough, a very thin layer, and we talk about how much work is required to pump that thin layer of water. So this is a thin layer of water. And in order to think about how much work is required to pump that thin layer of water, the most important thing is we need to know what the volume of that thin layer of water is. And so, when you have a rectangular solid, which is what this thin layer of water is going to be, you have the volume is always the length times the width times the height, right? So we have a length and we have a width and we have a height. So in this case, the height is really, really thin, right? It's basically the thickness of this water, and then the width is easy. That's the 10 meters. That's how long it is. The length is going to be the hard part. And so what we really need to do is we need to take a cross section of this, which is the picture you see down below. It's the second part of the figure. It's a cross section of this trough, if you will. And whenever you draw something like this, so you're going to have other ones in your homework and your notes. Whenever you draw something like this, you have to place your axes somewhere. And you can place it however you want. In the last problem, we placed it however we want. In this problem, it's probably going to be best if we put the bottom of the trough along the x-axis. So we can call this the x-axis, and the vertical axis right smack dab in the middle. And again, I'm going to draw in what the cross-section of that thin layer of water looks like. So if we have a very thin layer of water, first of all, since the thin layer of water is going vertical, the thickness, we can think of that as dy. And then what's going to be important is for us to figure out how far it is across horizontally. That is that length dimension that we need, right? We need to know the length of this thin layer of water. And the problem, and this is why we need the calculus, the problem with this is this width of this blue section we have here, it changes as the layers go up or down in height, right? Because the trough widens as it gets closer to the top. And it's going to change according to basically this side line over here, right? That determines it. And so what we really need to do is we need to think of that as a line and find the equation of that line. That's what we're going to want to do. So let's go ahead and think about this. To find the equation of a line, we need 2 points basically, and so we have 2 points that are easy to define. We have a point up here at the top, and we know it's 1 meter across at the top, which means since the y-axis goes right down the middle, you're going to have a half a meter on each side. So this is going to have a x-coordinate of a half, or 0.5, and then the height of the trough is 1 meter, so the y-coordinate is going to be 1. Hopefully that makes sense. And then at the bottom here, the bottom of the trough is only a half a meter long, or wide, right? So that means you have 0.25 on each side, so the x-coordinate is going to be 0.25, and then it's right on the x-axis, so the y-coordinate is 0. And we want to go ahead and find the equation of that line. So let's see here. Find the equation of the line. So the way we're going to do that is from algebra, right? How do we find the equation of a line? Well, we first need to know the slope. The slope is equal to y2 minus y1 over x2 minus x1. And we just use those 2 points here, the 2 points that we found on the line. And so if we subtract the y's, we can take 1 minus 0. And then if we subtract the x's in the same order, we're going to have 0.5 minus 0.25. So 0.5 minus 0.25. And so you end up with 1 over 0.25, which is 4. So our slope is 4. And then we want to use the equation of a line, which is y equals mx plus b, right? And we can put in all the information we know. We know the slope. And we can use either point. I'm going to use the 0.51 point, and so that means y is 1, right? Y is 1. Slope is 4, and when y is 1, x is 0.5. X is 0.5 plus b. And if you go ahead and solve that, it looks like b is going to be equal to -1. So that means the equation of our line is y equals 4x minus 1. Okay? So that's the equation of the line. Now, again, the length of this trough here, it changes according to the line. And so, any point on the line we can think of as a xy coordinate. And so in order to get to that point, you have to go over the distance of x, right? And you have to go up the distance of y. So if we're talking about the total length here, it's not just x. X is only half of it, because there's actually, by symmetry, there's actually another x on the other side, right? So the length of this trough is going to be actually x plus x, or 2x. So we need an expression, really, to figure out what 2x is equal to. And we get that from the line. We know that y is equal to 4x minus 1, which means y plus 1 is equal to 4x, and it means that x is equal to y plus 1 over 4. So if x is equal to y plus 1 over 4, then we know that 2x, so if we multiply both sides by 2, 2x is equal to y plus 1 over 2, right? If we multiply both sides by 2. And this is our length. So our length is y plus 1 over 2 because our length is 2x across. This is basically 2x there. We know that this dimension again is 10, and then the thickness here, this has a thickness is dy. So our volume of our layer of water, of our thin layer of water, our volume is the length times the width times the height. So it's what 2x is, which again, remember 2x is y plus 1 over 2. So we have y plus 1 divided by 2 times the width, which was 10 meters, times the height, or the thickness, which was dy. Okay? So, and of course the units here are going to be meters cubed, because we're in the metric system. We have meters times meters times meters. Okay? So, let's go back and look at the first page of your notes and remember what our formula is for finding work. So, remember, when we're in the metric system, well, just in general, work equals force times distance, but the force is going to come from the mass times the gravity. Remember, g is 9.8 meters per second, and then the mass, we're going to use density times the volume to get the mass. So let's go ahead and write that back in our problem. So our force is going to be the mass times gravitational acceleration. And then again, because mass is density times volume, we can say that the force is density times volume times g. And remember, we do know what those values are. So remember, we just review g is 9.8 meters per second squared. One thing I haven't given to you is the density of water, but the density of water is 1,000 kilograms per cubic meter, which makes sense why we should multiply density times volume to get mass, because if we take kilograms per meter cubed times our volume of meters cubed, we just get kilograms, which was the units of mass. So we got that, and we know our volume. So basically then we know our force, right? We know that the force is equal to our density, which is 1,000 times g, which is 9.8, times our volume, which is y plus 1 over 2 times 10 times dy. And of course, that's the force to lift up a thin layer of wire. So I really should go back here. This is really, right, this is really the volume for some layer, some ith layer. I can be any value between 1 and infinity, which means this is yi, which means this should be the force on that layer. This should be I, this should be I, this should be I. And we use calculus basically to get rid of all those i's. So the last thing we need to worry about is, in order to find the work to pump up that layer of water, remember, work is force times distance, right? So we know the force, and we can do the math on that. So if you take You multiply all this out. First of all, let's do this. I know that 2 goes into 10 5 times. 5 times 1,000 is 5,000. And let's do the math on 5,000 times 9.8. So 5,000 times 9.8, that's going to be 49,000. So I'm just simplifying this. This is 49,000. That's 1,000 times 9.8 times 5 is 49,000. And we have y plus 1 times dy. And I'm going to write the dy on the end. And we need an expression for distance. So we're thinking about what's the distance that each thin layer of water has to be pumped if it's pumping out the top. So the top, we know the distance from the bottom to the top is how far? How far is it from the bottom to the top of the trough? Well, the trough is 1 meter deep. So we know the total distance here is 1 meter. And we know that y is the distance from the bottom of the trough up to the thin layer of water, which means the distance, this is d here, the distance that we need to pump that water out is going to be the difference between the total, so 1 meter, minus the distance from the bottom of the trough up to the water, which is y. So our distance is not y, it's not 1, it's 1 minus y. So it's 1 minus y. Of course, this is the distance for each layer of water. And that's it. That's how we're going to find the work. This expression right here is the work needed to pump up 1 thin layer of water, and then we use the calculus. So the calculus says, okay, we're now going to integrate this. We're going to find the work by integrating 49,000 times y plus 1 times 1 minus y times dy. And now what is y changing from? Because this is, we're integrating with respect to y, and we know y represents the distance from the bottom of the trough up to the thin layer of water. So that thin layer of water can be all the way down at the bottom, and it's going to go all the way up to the top. So that range of values for y is going to go from 0 to 1 meter. And that's it. That's how we calculate the work. I'm not going to go all the way through evaluating this, but I would simplify this a little bit first. I'd first pull out the 49,000 because that's a constant. We have the integral from 0 to 1, and then I would multiply the y plus 1 times 1 minus y out. And when you do that, when you multiply y plus 1 times 1 minus y, I'm going to let you do that on the side, but that's going to simplify to 1 minus y squared. Check my work on that. And then you just integrate. It's what we know about integrating. We get 49,000 times y minus 1/3 y cubed, going from 0 to 1. And if you work that out, this comes out to about 32,667. And what are the units of work when we're in the metric system? Joules. So there is your answer. There is another example of doing this. It's a little bit simpler, but there's another example, example 4, that we skipped over. Make sure you review the solution to that I post in the lecture and go over and make sure you understand it. Like I said, there are examples of this in your homework and your notes. All right, that's the end for this video. Thank you.